It's possible.
Good morning, everyone. Today is February 22nd, 2020, and this is the John Chappell Natural Philosophy Society Science Chat. And let's see here. We didn't get an announcement today, so Ian tells me. So we might be a little bit short-handed, but hey, we've got one person watching on the on like YouTube, so or Facebook. So some people are starting to get on just because this talk is every Saturday at the same place at the same time. So we're hoping to gain an audience, that way. And we've got Ian in the live room, and if you'd like to join us in the live room, you can always go to where's our link here? It's live.naturalphilosophy.org. So you can go there if you would like to join in the discussion today. Now, I didn't have any particular topics today, so I'll start with you, Ian. I was wondering, anything's top of mind for you this week?
Well, always one or two things at the back of one's mind, I suppose. One thing which is quite tangential to anything we've been discussing recently is I happen to be looking at the question of viscosity recently, a variation of viscosity with temperature. And obviously for liquids, the hotter they become, the less viscous. I mean, we all know the situation of molasses or treacle in January being very, very thick, and then in June it flows, and the same with the oil in your engine in your car. But on the other hand, for gases, it's the opposite. It's inverse. I mean, the higher the temperature of a gas, the more viscous it becomes. And
is that true? I never heard that.
Yeah, I had to look it up actually twice because it sounded counterintuitive. I think I looked it up in Jean's Dynamical Theory of Gases last, and he seems to verify it, yes. So I don't know what the explanation would be. I haven't really thought.
The problem with that is that gases themselves are things with very little viscosity.
Yes.
Not really any that you can really measure, or that viscosity would have to do with, the pressure. But I've never heard anything about the heat.
I don't have the table in front of me. I could get the book, but even though they weren't very viscous, there certainly was a variation, a sensible variation with temperature. And it possibly could have some technological applications, which I'm not aware of at present.
Okay, well, that's an interesting factoid, and I don't think we realized it does the opposite as liquids. I wouldn't think that. I would have thought that heat would have had exactly the same effect on gases, which is to make them less viscous, because you'd think that heat would weaken the bonds between individual molecules.
Yes, and because the molecules are moving more rapidly, there would be less friction, presumably, internal friction, which is really what viscosity is.
So were you interested in that you want to know why it does that, whether there's such a dependence?
Yes, I mean, it wasn't a major thing, but I happened to stumble across it just the other day, and it was in the back of my mind that, if we're stuck for a bit of a conversation, I might raise it, because some of you guys, I think, are a little more concerned with sort of physical models than I am. I'm a bit more of a theoretician, and I think somebody like you, Franklin, might sort of be able to home in on a sort of a reasonable explanation more quickly than I. So I didn't really give it much thought. I said, I'll raise it if they say, we're at a bit of a loss to discuss something.
That's right. If I put you on the spot and ask, what's on the top of your mind? But yeah, that's totally down my alley, which is because I'm very much a physical modeling kind of person. You see, my shtick is that I don't believe anything you can't explain on a billiard table, pretty much, right? If you can't explain it on a billiard table, then I don't believe it, right? But if it happens on a billiard table, then I'm pretty convinced it's probably okay, right? So, but sticking with the billiard ball tables, it's like, and you're talking about viscosity and what it really means, you know, in terms of a billiard ball table, that would be like, you've got your billiard balls, and then you've got like the thing that you rack up the billiard balls with, but you know, you fill up the billiard table with like lots of billiard balls, like 70-80% full, and then you try and drag your rack through the billiard balls, right? So depending on how many billiard balls there are there, it's going to take various amounts of force to drag your rack through across the table, I suppose, right? So you can imagine that. So that is kind of just, you know, independent of temperature, I suppose, is kind of a way to think about viscosity. So the more particles that you have per unit area, the harder it's going to be to drag that rack through the billiard balls. So, but I'm not quite sure that has to do with, say, the whole heat thing, because the heat thing is the difference of either the billiard ball being still or the billiard balls being all jostled around, right? Like you just shaking
one of the keys might be what you said earlier. I mean, in a solid, well, you're just increasing the temperature, and that's just one parameter. But in a gas, you're actually increasing the pressure as well. So maybe a better way of looking at it is that the viscosity increases for increasing pressure on the gas.
Well, that's what you would think, although you were kind of saying the opposite effect happens. So that like I said, is surprising on that basis.
No, not the opposite in that case. In the gas, the higher the temperature, the higher the viscosity, which seems counterintuitive.
Yeah,
but the higher the temperature, the higher the pressure.
That is true as well. If you have a container that is restricting a certain amount of gas, then what changes is the pressure. Of course, if you had gas in like infinite space, then I think if it was allowed to, I don't know, go anywhere, then probably it might not necessarily increase in pressure, because temperature is really a measure of velocity. Because I was surprised that when they tell you how fast is like the air molecule that's moving around the head in your 70-degree air. Do you know how fast each molecule is going?
I may have calculated it once, but I have no idea.
It's surprising. It's something like 3,000 miles per hour on average, which is just humongously fast speed for a molecule. You know, that's like way above like the speed of sound, isn't it?
Yes.
And then there have been discussions as to, you know, how fast can a fart go from one side of the room to the other, and if the molecules are going 3,000 miles per hour, it'd be nearly instantaneous, right?
Right.
So that's kind of the funny joke, physics joke. Yes, how fast can a fart travel from one side of the room to the other, right?
But it's still a small fraction of the speed of electromagnetic radiation, of course.
Yes, but it's still remarkably fast. I mean, they don't go that far for very long because it's just this chaotic system where the gas molecules are doing like this Brownian motion, and they just go a short distance, and then they go a different direction, and they're just bouncing around like crazy. And in general, they probably don't go very far. But if you've ever seen Brownian motion, but the individual speeds are apparently still quite quick for a gas. But
I would have expected them to be reasonably quick. I mean, not like a very small diffusion of electrons through a copper cable, you know, where you're just going, I don't know, fractions of a meter per second or something, very, very slow. I would have thought the molecules are going rather rapidly.
Yeah, they are. But getting back to, say, your original question, so, you know, you can go from, say, a solid state to a liquid state to even So if you take something like cooking fat or something, I guess like that, or or even just motor oil or something like that, it can be very thick when it's very cold, and then as it warms up, then it gets looser and looser and looser, right? It less viscous as it goes along. So I mean, I think it is an interesting question as to why does it do that, right? And I suppose we've already touched on what we thought might be the answers, which is that as you add energy into the system, the relative motion of the molecules is going to increase, and any natural attraction that each molecule would have a more difficult time because they're speeding past each other faster and faster to the point where where whatever causes that stickiness fails to work. So, but getting back to say my billiard ball example, you'd have to add the property that the billiard balls are kind of sticky to each other. So let's pour glue all over all the billiard balls and then start moving those around, right? And so if they're not moving around very much, then it's going to be really hard to drag your ball rack through the sticky balls, right? But if the balls are moving around very rapidly, then the balls will have less chance to stick to each other, and then you'll be able to move the rack through easier, right? Now,
so getting back to the motor oil business, what nature would the additives have that they put into motor oil to reduce the reduction in viscosity with increasing temperature?
I don't know. I don't know if they actually put things like that to change the viscosity, or what ingredients they have available to combat loss of viscosity. Because obviously that's probably an important thing, because you don't want your motor oil to get totally thin when it's running in the engine, right? That they probably work very hard to prevent that. But that's an interesting question, but I've never really understood additives in motor oils. So other than there may be such things, right?
Yeah, well, multi-grade motor oils, it obviously is an engineered product, and it's a composition of various elements.
Yeah, what is 5W20, right? It's a combination of 5W and 20 weight oil. I mean, is it really just a combination? Because when they distill oils, they get different products at different levels corresponding to different molecular weights. So, and it may be that be interesting to see what the difference is between the 5W and the 20W. Is it just it has higher molecular weights there? I'm guessing it's probably the thicker oils have higher molecular weights with the larger overall carbon chains, because we're talking about hydrocarbons here, and those things are just chains of hydrogen and carbon, and they can be longer or shorter. So like the shorter ones are things like gasoline, and the longer ones are like grease. It all comes out of the same thing, and it's all made of the same stuff as well.
Right, and they also don't want the oil to be too thick at 0 degrees, say. So it's engineered at both say freezing conditions and maybe a couple of 100 degrees or something, whatever your engine is working at. But as you say, they're all hydrocarbons, are the same. They're really mixtures, I think, of various compounds rather than sort of chemical reaction giving a different compound.
Yeah, I think all these hydrocarbons are like a million variations on the same thing, pretty much. They all have really different properties. Like gasoline has a lot of different properties than grease, but pretty much carbon, oxygen, nitrogen, that's pretty much it. Hydrogen, that's what all hydrocarbons are basically made out of. But I think getting into the physics, what is the physics that we're talking about here that makes the differences between, say, liquids and solids? mean, that is actually a ongoing conversation of topic in the email as to, say what is the actual difference between, say, what is a solid and then what is a liquid or a gas, and what are the properties of that. Now, for me, I say a solid is defined by the nature of the bonds of material, in that those bonds don't want to change, that whatever bonds you have remain in the same geometric pattern at all time, irrespective of, say, external kinetic energy. So if I have my pencil here, it's solid because the bonds in the carbon and the oxygen and the nitrogen, which is exactly the same elements in hydrocarbons, have arranged themselves such that they do not change position. And one of the characteristics of, because they don't change position, it does not allow other solids to pass through it. So my finger is not going to pass through this pencil because the bonds in my finger are pretty much in fixed place. The bonds in the pencil are pretty much in fixed place. And because they want to stay that way, they meet what we feel is a solid and hard surface, as opposed to, say, we've got, the liquid in my cup here, right? So if I put my finger in there, it just goes right through. I mean, I barely feel it, right?
Well, again, temperature is the key, because a solid is just a frozen liquid, and a gas is just a vaporized liquid.
Yeah, I suppose water might be a good example of that. So water, room temperature, liquid. But you freeze it, and then it becomes what is a solid. Or if we boil it, it becomes what we call a gas. So this is a material that can take, all three states. And we can see what the properties are. So when water is a solid, then it acts just like the pencil, that, I cannot put my finger through it, right? So definitely the state is not anything, not a property of the type of material. The type of material can take on all three states. And there's another state that people like to talk about, which is plasma, I guess, is another state. So if we took the steam and we injected a lightning bolt through it, then some people like to think that that's a different state as well. Plasma.
Because of ionization and so on.
But this has come up in, for example, discussions about like what space is made out of, right? So, there's those of us who believe that space is made out of material substance, and that that material substance is a sea of charges. So there's several of us who would all agree that, yeah, there's some kind of a positron electron sea out there. So the question is, what is its structure, right? So some people, like the E-polar theory, say that it is a crystalline structure, just like salt, which is a very ordered structure of just positron, electron, cubic lattice, and they claim that space is made out of that. And now my difference is that I believe that space must be a liquid, because we observe that, yeah, I can put my hand through this space and it doesn't seem to be impeded at all. I would say that if it were a solid, and if that solid was made out of the same kind of matter that, say, my hand is made out of, and if it's made out of positrons, electrons, and indeed it would be, then it would probably have to obey the same laws of solids as we see for everything else, which is that it would be like the frozen cup of water, and it should not allow the motion of other solids through it. So I would argue that space cannot be a lattice, right? It would, if it were, then it would impede the motion of everything. I mean, literally stop it. Everything would be frozen in place if that were the case. Versus a liquid, I think, is just a lot more possible, right? It's kind of hard to keep something in a stately ordered lattice like that. So not only the problem is that such a space would be completely solid and would block all motion, it's from an entropy standpoint a lot harder to maintain, because that's, you know, a very low state of entropy versus like this glass of water, which is a high state of entropy. I mean, it's like high, almost as high as the atmosphere around it, where everything is just flying around, bumping into each other, Brownian motion. And the amount of energy that's contained in the glass is reflective of its temperature, right? I also kind of think that space may also be that way as well, that the amount of energy available in space is kind of a measure of its temperature. So, for example, here in my room, I would think that if there is an ether, and if it is material, and if it is a sea of positrons and electrons, that it's got more energy here down in Earth than, say, the far side of the moon, where it's minus 200 Kelvin or something like that. So in some ways, I think maybe it can hold energy, but but that's just kind of a tangent about what's a solid, what's a liquid, and what's viscosity, which is kind of a scale on that whole thing. The other thing that came to mind is that I think this whole question about viscosity is also related to what we think mass is, in that just like it's like if you take a spoon and you run it through molasses, that presents a great deal of resistance. And you take a spoon and you move it through water, and that is much less resistance. And in terms of what we call mass is just basically the resistance to acceleration. We get mass as part of the formula for force equals mass times acceleration. So, and then mass is equal force divided by acceleration. So mass isn't actually a property of the object itself, right? So if I have a marble, the mass of the marble isn't actually a property of the marble. It's just a property of the resistance of the marble to acceleration. So it's like an experimentally derived value. So the mass of the marble could be anything, right? So if you measure the mass, if you measured, I don't know, if you measured, say, the mass of the marble and it is through molasses as the resistance to acceleration, as we commonly call it, then you would find that the mass of the marble is much greater in molasses than water, right? That's just what I'm trying to tell you, trying to understand what mass actually is. It isn't a property of the marble. It's a property of the marble against its surrounding medium. Do you agree with that? That's an important point I think I need to get across to people. That what we call mass is not a property of what I call the matter. Okay, you've got matter. Matter is like a marble, but mass is just something that we measure as a property of movement against the medium that that marble is moving through.
I certainly have a response, but I'm just wondering, is there anybody here at all? There are no comments, no pictures. I thought I saw James flash up. I may be wrong.
No, James is here.
Oh, he is.
Hi, Ian.
Hello, James. I was hoping that I'd have a little help, from your dulcet tones, rather than have myself and Franklin just hog the show.
No, we thinking this was going to be the Franklin and Ian show. So now it can be the James, Ian, and Franklin show.
Let me
So
turn down the light here.
James, you have
The way
any
I turn
comments
down the
about?
light is by closing the curtain a little bit.
Well, I'm the opposite. I've put on my light here because it's, sort of mid-afternoon and the sun is going down shortly. So
There. Okay, so I'm not so bright there. At any rate, part of my interest, as I've said on occasion in these chats, is to learn the perspectives of others, like of Franklin and of Ian and other participants that come here. And so occasionally I might throw in some of my thoughts. Like, for example, when Franklin was talking about how we evaluate mass, I've had to come to the conclusion by calculating the proton-electron mass ratio in my simulator program that we really have, in my opinion, two quantities that we might call mass. And one is my energy quantization, which goes along with the length and time quantization. And that would be an invariant constant. And you can express that in kilograms or in electron volts as you might like. But if you express it in kilograms, it certainly has the units of what we normally call mass. Now, I found very interesting, and at first I thought I'm doing something terribly wrong with my software, the simulation program. But I had to finally come to see that the proton-electron mass ratio, which is about 1,836 and a few decimal points there in addition, actually depends on quanta density in the simulated volume. Like the cubic lattice that Franklin just referred to a few moments ago. I work with a cubic lattice as well. And if there are more one state, what I'm calling quanta or one state bits, as opposed to zero state cubic elements of the cubic lattice of the universe, if there, we say that the energy density is increasing or decreasing. So, like, for example, absolute vacuum, which is distinct from perfect vacuum now, absolute vacuum would have zero quanta in the volume. And then, of course, there's a maximum possible quanta. Now, I found that the proton, and here's the punchlines, if you're wondering, well, when I'm going to conclude this little comment here. The punchline that I found was that the proton-electron mass ratio depends upon energy density. Okay, so, and in fact, where we get the observed proton-electron ratio is about 0.25. In other words, about 25% of the locations, or bit loci, as I call them, contain energy quanta, which are one state bits, 25%. Yeah, when I calculate alpha, it's also the same thing. Now, what happens with this second definition of mass, which is variable? Okay, if we reduce the bit density from 25% that I just mentioned, in that environment, the proton mass, or which is equivalent to saying the proton-electron mass ratio, since the electron mass is constant, the proton mass decreases. And if you increase the bit density above the 0.25 mark, the proton mass increases. And by the way, it's not linear. Okay, so in fact, we have two in my work, and it might be useful for anybody based upon their whatever theoretical point of view they might wish to pursue, that we might start thinking about two definitions of mass: an invariant value, which is sort of an amount of energy, okay, or what I'm calling an energy quanta, a one state bit, invariant. Okay, it doesn't depend upon velocity or anything else. It's a primary constant of nature. And the second definition of mass goes with Newton's law, as Franklin was just describing, force equals mass times acceleration. In other words, It's a resistance to movement or likelihood that an object will move given a certain force environment that it has. So that would be where I would chime in terms of what Franklin was just talking about. That I think what he's saying does make a whole lot of sense in terms of the work that I found. Because at first I wanted to derive, I've worked on deriving various constants like speed of light, etc., and Planck's constant and so forth. So I wanted to derive the proton-electron mass ratio, and to a certain extent I failed because I found that ratio depends on energy density, if you will, in the simulated volume. That it's not a constant, that the ratio that we observe is about 0.25 or 25% of the maximum possible.
Well, I suppose the question would be, do we have experimental evidence that the proton-electron ratio can vary? Because if it could, then that would be more in favor of your theory, because you're saying that that ratio depends upon the environment that space is made out of. And
exactly. I'm working on collecting my thoughts about this in terms of and almost an Archimedes buoyancy concept of gravity. In other words, if you go to a lower bit density environment, say away from the Earth's surface and our normal standard temperature, pressure, laboratory, or sea level environments that we talk about so much, we even have heaters and air conditioners and all sorts of things to try to maintain that constant because we're very comfortable with that as a species. But as we move away from the surface of the Earth to outer space, guess what? Things are more buoyant.
Buoyant in what sense? I mean, there's no sea.
Well, in outer space, the bit density, the overall energy density might be decreasing. And
I'm thinking it might be as well. I mean, I think it's kind of interesting.
Then my work is showing that the actual mass, the number of kilograms you and I weigh when we're up in the space station compared to here on the surface of the Earth is actually different. Is actually less. As a matter of fact, it's so much less that we're floating around in the space station.
I'm not exactly.
I haven't totally formulated these ideas in a systematic way, but what I'm saying yet, I'm working on that. But like it's the takeaway message is that mass is defined by Newton's law of force equals mass times acceleration seems to depend upon the energy density of the environment of the object. Okay, it's not like a fundamental constant.
Well, I think that's what I was trying to say, that mass is not constant. I mean, to the point where there's some experiment saying that the mass of the electron, say, isn't constant. Depending on its environment, the measured mass can come out differently. So that's what I mean.
Let's talk about the motor oil.
Itself,
like if you increase the temperature of the motor oil, I'm sorry to interrupt you, Franklin, but it's just to chime in here to get right back to you. We were talking about the motor oil before, and I thought, well, that's a bizarre topic for Saturday morning. But let's talk about that. How about as you decrease the velocity by increasing the temperature, in my parlance of what I'm talking about, you're increasing the energy density in the volume holding the fluid. There's more quanta of energy in there with more heat, as the thermodynamic people would say, when the temperature goes up. So there's more energy in there. And what happens? The viscosity goes down. The resistance to movement goes down. Because when you move that spoon in the oil, you're actually moving the oil on one side of the spoon. And its resistance to motion is less. Period. But that sort of links together what I'm saying with what you were saying, Franklin. There's no disagreement there. It's just a little bit of data that I'm adding, my observations that I'm adding, and it
Mhm.
agrees
Well,
with what you're saying.
well, I find it interesting that you have the concept of basically the density of space. So you're saying that at 25% maximum density, you can calculate out the observed properties, the generally observed properties of protons and electrons.
And
And
also alpha,
what is
which would be
alpha?
the big payday. It turns out that alpha, we get the value of alpha is the probability of an electromagnetic, which I call a scalar or vector force event in my work. That depends upon bit density.
What
Because the
exactly is
potential
alpha?
bit has to
I'm
be.
not. I've not heard of this alpha thing.
Is this the fine structure constant? I'm not
Yes,
sure.
alpha. Right, excuse me, I should have said that because alpha could be anything, right? Sorry,
Yeah, it could
my
have
bad.
been beta, could have been omega, could have been, I
Exactly,
don't know.
it could have been alpha particles or whatever. Yeah, I'm talking about the fine structure constant. It turns out that that depends upon bit density as well, because it's sort of the likelihood that a one-state potential bit would be adjacent to a one-state source bit, which that potential bit would cause to move if the destination locus is empty. And
But
that's
what
basically
exactly
going
is the
on in the
fine
pool.
structure constant? Can you
Excuse me?
explain what that
Well, that
is used for?
that's what they call the coupling. Well, it has many applications in physics, as it turns out, but it's basically the coupling constant or the in the electromagnetic interaction. It's a coupling constant. It's sort of like gravity has a very, very weak coupling constant, supposedly, if you believe in those theories, which I don't. Um, uh, the strong force supposedly has a much greater coupling constant, and therefore it's stronger. But it's basically the coupling constant in, or the probability that an interaction will actually occur. Okay, you could look at it that way.
Okay, 'cause I've heard the term, but never really understood exactly what that was. So now we do have
It's just as simple.
we do have Dr. Lucas watching us here on YouTube. He has some comments here. Let's just take a look at that. So he's got some things. So he's managed to predict the mass of all elementary particles to 1%. Now that's interesting because you would obviously be using a different methodology than James, I would imagine. But I think this is actually kind of common amongst dissident theories in that they all predict things, and now it could be that they're all predicting the same thing because they're post-dicting. So if you know what the target you're looking for, there's always ways of changing your theory to hit it, right? So, or they actually did predict the mass. I'm just throwing that out as a general criticism.
Or for Dr. Lucas, we could say, is he also predicting that the mass of, he says, all elementary particles, take any one of them, say the proton, does it change with temperature? Because temperature basically is correlated with bit density. The more you increase the bit density up to a point, by the way, it's not all the way up to 1, but or 100%. But the more you increase the bit density, the temperature rises by definition. Because
Well, I was kind of wondering, does say a vacuum, can a vacuum have I guess, a temperature? Because now typically we consider temperature to be the motion of the matter particles that are in space. But if you take a jar and you remove absolutely all the tangible atoms in there, can that be said to have a temperature? Now, I would say
yes,
yes,
I
because you
believe
could stick
so,
a
yes.
thermometer in there and it'll register something, right?
Because I'm showing that perfect vacuum in my work, which is not perfect. A lot of my work is pilot studies that need to be reproduced and larger samples and so forth and so on. But one of my most recent articles is a vacuum composition showing that 88% of perfect vacuum is energy quanta. In other words, if there are particles at absolute zero temperature, okay, so there's no electromagnetic radiation in there, there's no particle movement in there because we're at absolute zero, okay? And the simulator run in vacuum mode. If you just download the simulator and run it in vacuum mode, you'll see that energy quanta are leaving that space, the simulated volume that you've chosen, and they're not restored. And it gets to a certain point, and that's it. So the remaining quanta are what? Particles and the perfect vacuum when we subtract out the quanta associated with those particles, which is exactly what I did. And so what percent of the total quanta at absolute zero is perfect vacuum? 88%. In other words, most of the energy quanta is not the particles at all. It's the perfect vacuum, which, by the way, everyone is talking about is empty space. It's not empty at all. It's teeming with energy quanta, according to my work.
Because there's a radiative transfer as well as a convective transfer. So in other words, if you minimize, either to zero or to a very small amount, the convective transfer by having a sort of a perfect vacuum, and therefore maybe in conventional terms we have an undefinable temperature. The temperature of convective temperature of outer space is undefinable. You still have a radiant transfer, a possibility of radiant transfer of electromagnetic radiation between maybe the thermometer put inside this perfect vacuum and the external environment. So there's still a net heat loss or a heat gain, which will affect the reading on the thermometer.
I mean, really?
Now,
that would be the experiment I would do. Is like, because if you have, like, say, a thermos bottle, those things, stop the flow of heat energy entirely. So if you stuck a thermometer in the middle of a vacuum flask, what's it going to read, right? Is it going to just maintain the temperature that it was when you stuck it in there? Or is it going to take on some other value that's dependent upon the outside environment of the vacuum? I mean, I'm imagining that, if you took a thermometer and it was reading like, 70 degrees and you stick it in the vacuum, that it would continue to read 70 degrees no matter what. And if you put it in when it was reading 0 degrees and you stuck it in the vacuum, that it too would remain 0 degrees, even if the outside of the container was like 200 degrees or something. Because that's how vacuum bottles are supposed to work.
Well, you're putting the temperature in the center of the thermos flask rather than in the vacuum walls. But I mean, these units are not perfect. Obviously, there is some leakage. So it'll maintain the temperature for a very long period of time, irrespective of the temperature outside the vacuum wall. But ultimately, there will be some convective transfer and some radiative transfer. And over an infinite time, the temperature inside the thermos flask will be the same as the temperature of the surrounding. It will degenerate to that.
It seems like somebody with a vacuum pump in the right kind of container could do this experiment. Stick a thermistor or thermometer of whatever type you want in the middle of a container, and hook up your vacuum pump and start pumping the gas out. And the closer you get to perfect vacuum, I would think the temperature would drop because, I would think that. Now, in terms of the cosmic background radiation, I'd like to pose this as a question, because I would hook that up with what we're talking about by saying that's apparently, or at least people claim it is, a measure of the temperature of far outer space, which is fairly close to perfect vacuum, in the sense that there are very few atoms there, and the few that are there are probably mostly hydrogen and helium.
Well, I personally think that since I think space is a substance that's moving around, that inherently it should have some temperature, right? That you could actually potentially change. So, that's kind of going along with maybe what James is saying, that space has maybe this variable property of some kind of absolute density, and you can get the properties of the mass of the proton and electron off of that, right? Although I'm just curious whether, James, you can explain without using math, but more in an intuitive way to like an intuitive physical person like me, why is it your simulation is coming up with the proton being, nearly 1900 times more resistant to acceleration?
Oh, okay, that's a good question. I'd be
The
glad.
electron.
Here's the sort of the no math version. The only thing that we're going to need is just a little taste of geometry. My program outputs with every tick, which is a cycle of bit operations, of which there are 4. It outputs the position of all of the quanta, sort of the center of mass, if you will, type of calculation. The center of mass or center of bit, if you will, position for the proton bit cycle and for the electron bit cycle separately. So with each tick, I have 2 positions. Now I can measure, I can also, and the program also outputs this information in a file that you can just load into an Excel program or other spreadsheet program and just look at it. The change in position for both all of the quanta in the electron bit cycle and all the quanta in the proton bit cycle. Okay, so the only math I'm just putting in words like on your billiard table. We could say after a certain period of time, the white ball, which we'll call all of the electron ones, have moved to a new position, and so therefore the displacement, the amount of movement, the distance of movement is just simply the subtraction of those two values. Then we could look at the dark billiard ball, let's call it a dark one, for the proton center of mass, all of those quanta, and it moved a certain amount. So now I have, with every single tick of the simulator, how much the center of mass of the proton quanta moved and how much the electron moved. Well, the ratio of those two is related to your proton electron mass ratio. Typically, what you find is that the lighter thing, the electron center of mass, moves a lot more than the proton one. And I think this is because the electron bit cycle is a very simple one located in a spatial object I call a spot, just a single spot, with only 6 locations in it. Whereas the proton one has 42 locations. It's a much more complicated cycle. And so it's more difficult to move it, if you will, if you just want to say that intuitively on that basis.
But there's acceleration involved here. So you have to be able to...
you can view each displacement as a certain amount of movement, momentum, or acceleration during that time period of one simulator tick or time cycle. And so that you can compare how much each moved. If you make the big assumption that any electromagnetic fields in the simulated volume are going to affect the protons and the electrons pretty much the same, although the sign would be opposite, but because of the opposite charge. But you can just say, oh, okay, so my force is acting. I'm just going to assume they're pretty much the same for all of the quanta in the electron cycle and the observed displacement there, and all the quanta in the proton cycle and the observed displacement there. What I find is that at about 0.25 of maximum bit density that I alluded to earlier, we get the proton-electron mass ratio.
So, but basically, you're saying that it's a complexity of the proton that gives it the greater mass. So
yeah, it's harder to move.
So in your simulation, you probably just say put a proton in space put another proton in space, you have an accelerating force present. And you'd find that the electron, it goes much further distance than the proton. Basically, that's what you're
Yeah, I'm comparing at time 0 and time equals 1. Let's say, how much did the center mass of all of the electron quanta move? What's the displacement? That's just a number. And how much did the proton move? Now, if you divide the amount of movement of the electron by the amount of movement of the proton, because the electron is going to move more, you're going to get a positive number greater than 0, and that with a constant, a proportionality constant that I worked out, you're going to get your proton electron mass ratio, and it does depend on density, okay, energy density in the volume. It's not like an invariant constant.
Mm-hmm.
So in other words, if you go up in the spaceship and properly measure the mass of that 1 kilogram, it's not going to be 1 kilogram up there.
Now we have some comments from
of the environment is less. In fact, the mass of a hydrogen atom out there in far outer space, where it's mostly perfect vacuum, is going to be very close, not that much more than the mass of an isolated electron.
Well, let's see. We got some comments from Bill here. So, Bill says that we need to be able to predict the mass of 100 elementary particles. So is that meaning that, because obviously we've measured these things, I guess, that's probably a problem in the mainstream of 100 elementary particles? Although I'm not 100% sure that there are even that many. I wasn't aware there are that many. Now, I personally think that the elementary particles are just basically the electron, the proton, the neutron. And we have all these other more exotic particles that don't last very long. So I don't consider those elementary. If they don't stick around, then for more than a fraction of a second, then I don't really consider them to be anything elementary, I suppose. So, and he does it. Oh, let's see. James, you're muted here. So.
I'm sorry.
I see you trying to talk there. So I think, and he does agree that mass would change with velocity or temperature.
That for a proton to move, the bits in the proton bit cycle have to exit that cycle and go into another adjacent proton bit cycle. I'm thinking that in agreement with what the spirit of what Franklin just said, that a lot of these exotic particles that have a very short a lifetime are in fact the transitional states of proton motion. Okay. End of story.
Yeah, what are they? I'm just questioning whether there's 100 things you could call elementary, I suppose.
Just a point about the mass changing with velocity. I'm just querying maybe Bill and so on, or just raising the point as to whether it is conceived that the variation would be according to the Lorentzian or relativistic type formula. The other point I was going to raise is that we define mass, as the inertial reaction in a vacuum or in the ether, if you like. So we impress a force upon an object, we measure the acceleration, and then we get the mass. Now, and then when we do the same experiment in a viscous medium, we attribute viscosity to the medium. We say, well, the ratio of the shear force to the velocity gradient would give you a sort of a coefficient of viscosity. Now, we could easily have a variable mass. We could say, well, I think you referred to this earlier, Franklin. We could say, well, the mass would be apparently much greater, and therefore there are no special viscous coefficients that we need to take into account. So the conventional Newtonian conception of mass is a proportionality constant which applies in free space, and then we have to account for other properties in other media.
Well, you talk about viscosity and relativity, and I kind of feel that effect where, in mass, apparently there's a mass increase. And so they say that, the mass is larger in a gravitational field, right? Versus away from a gravitational field.
Well, the weight is greater.
Maybe no, actually not really the math, but we've got clocks run slower in a gravitational field, which is a relativity effect. Now, if you think what a clock's like a grandfather clock. You've got a pendulum that's moving back and forth in space. And I'm thinking that, well, the reason why I say the clock slows down is because it's like the difference between having your clock run in water versus running in molasses. So if your clock is running in molasses, it's going to be slower, right? That clock is going to run slower than if you put the clock in water, it would run faster. And if you put it in air, it would run faster still. So what we're talking about here is, in terms of the clock slowing in gravitational fields, I think is actually a viscosity property, right? That towards the closer you get to the gravitational field, the more compressed the space becomes, and it's more viscous, right? So that's kind of how I feel what the explanation for this relativity effect of the gravitational clock slowing, right? And I think
again, if I may jump in here, Franklin, I would agree with you in spirit and say that actually what you're talking about in terms of a change in the viscosity in relation there, in your comment just now, is a change, what I would call a change in quanta density or vacuum quanta density. And basically we're saying the same thing, that if the density is higher, it's a little more difficult for things to move. Whereas if the density is less, there's less resistance to movement. And so that's what, and when you think that we don't have empty space, so whatever change of state of a cesium, what is it? Cesium 133 that they're using in a lot of these atomic clocks.
Yeah, atomic clocks.
For it to change its state back and forth, remember, it's not an absolute vacuum. I don't believe in that. There's a lot of energy quanta there, in and around, even within the atom of the cesium. Within the cesium, how do you pronounce that? My God, I can't say
I think
it's cesium atom.
Cesium.
So that with less density quanta in the so-called empty space, which is not empty space, the cesium is going to have less resistance to change its states, so that quanta density, or perfect vacuum density, because we're rejecting the empty space concept completely, with a sort of similarity to what Franklin's expressing, that he thinks if there's something there, there's a bunch of particles or something there, and those I would call my energy quanta, would affect the clock rate. You don't need special relativity for that. Okay?
Well, I think special relativity is just kind of an empirical observation that we've seen. Now the question is, how do you explain it? And it's like, you're right. It's like, we're talking about the same thing. Your model just has a specific implementation of that. Or it could just be like billiard balls. Like I said, I appreciate you bringing your work down to billiard balls so I could understand it, right? So it makes it much easier for me
but
to
it's
do that.
interesting. I mean, for a person, including myself, who rejects the basic tenet of special relativity, that the clock retardation in a gravitational field, or because of difference in velocities, it appears to accord with the Lorentzian term. It's the same formula, in other words. And some people have thought that's a bit of a coincidence, but it can be maybe rationalized in terms of viscosity in one case, or maybe the sort of C plus V into C minus V in the other case.
So what do you mean exactly by, you don't like relativity or so? What exactly?
Well, I reject, for example, length contraction. I think that's a fantasy. And I actually reject time dilation as well. And I'm probably not surprising anybody here. I would be surprising people at a more conventional forum.
Well, time dilation has been experimentally shown to happen, right? That's pretty easy to show.
This is what we're getting at. I don't call it time dilation. Time isn't changing itself. Time is absolute in accordance with my theory. And I think, a lot of us have sympathy with this. But we know, and it's what you're referring to, no doubt, we know that clocks vary. Atomic clocks anyway vary, depending upon the gravitational potential, and also depending upon the difference between the clock and the speed of the clock and the speed of the detector. But furthermore, the variation would appear to be the same as the formula given by special relativity, which is based on the Lorentz term, the contraction term. So that leads a lot of the mainstream to say, well, that proves that we're right and you're wrong. But many of us would say no. The tenet of special relativity has been disproved, and there isn't.
Well, I think I call that clock dilation, and rather than time dilation. Would that be a more acceptable statement to you?
It would be more acceptable to me in the sense that it's attributing the behavior to the measuring instrument. Whether in which case it's dilating or whatever, rather than time itself. It would be one way of expressing it in shorthand.
Yeah, because I think that's the main difference. That what we're really talking about here is clock dilation here, something that happens to a clock, not something that happens to, I don't know, time in general. Because, even though that clock over there has been dilated and slowed down, that has nothing to do with what's happening with the rest of the universe.
So in the case of motion, it's the 1 minus v squared over c squared term. And in the case of gravitational potential, it's the sort of like the g over c squared, term which comes in. And I suppose somebody like me would say that is an etheric effect rather than that it is a special relativistic effect. But it's gh over c squared. It's the ratio of the potential to the speed of transmission within the medium.
Mm-hmm. Although I still have some comments about what exactly is an atomic clock. And while I'm not a complete expert, my claim has always been that if the clock were actually based on the actual electron transition from one position to the other, then that would actually have to run at what I consider the absolute quantized time, because the amount of time it takes for an electron to move from one position in space to another is actually, say, as what James might say, is that is a quantized amount, which is a constant. And that if you built a clock out of that would be completely immune to any of these relativistic effects. So the question is, why is it an atomic clock is not immune to these effects? So these atomic clocks are vulnerable to changes in gravity and in velocity. But in my research, I find that ultimately what an atomic clock is actually counting are the vibrations of a tuning fork, because at the heart of every current atomic clock is in fact a quartz crystal, just like in your watch. And the quartz crystal works on exactly the same principle as a pendulum in a grandfather clock. It's just bigger, right? But ultimately, it's actually a fork that's moving through space physically in a macroscopic sense, right? And that the atomic part, from my understanding, all of that is being used as just a feedback loop, so that if that crystal slows down a little bit, and the atomic feedback loop speeds it up. And so that's really that's what's really doing. It's just acting as a feedback loop to make sure that the crystal slows down, that it will get sped back up. And that makes for an exceedingly stable crystal oscillator, but it's still ultimately a crystal oscillator. It's not an atomic-based clock. But I understand that they may actually be working on these clocks, which might actually be based on the speed of the actual transition. You know, something like a laser clock. It's something that doesn't have a quartz crystal in it, right? That's actually basing the clock off of the actual wavelength or frequencies that are atomic. So, but one of my predictions would be is if they ever actually managed to make a clock like that, I would predict that it would be completely immune to these relativistic effects, and we would find that it would tick exactly the same, no matter what gravity field you put it in, and no matter what acceleration you take it at, it would tick exactly the same. But I don't know that they've actually done that, but that would kind of be my prediction.
And furthermore, would you predict, Franklin, that if you had a conventional clock which is affected by gravitational and velocity effects, this crystal, say, and you do put it out into some area of the universe, you know, you sort of perform the twin paradox experiment with it. Well, do you predict that although there would be in its motion variations in the time it reads in comparison with a timepiece on the Earth, but do you predict that when it returns to Earth, it would resynchronize with the clock on Earth?
Well, it wouldn't resynchronize in the sense that it would show a different time still, but it would resynchronize in the sense that it would start running at the same rate. So, and the clocks would no longer drift, because that's what's happening when you have the twin paradox. You go send one clock out there, you get the clocks drift, and there's a rate of that drift. But when you put the clocks back into the same environment, then you would see that there's no more drift. The drift would stop.
Oh, okay, that's easy to see. But if there would still be a net difference because of the history of the clock,
there would be a net difference. That difference would always be there. So
okay,
it's not like you bring the clock back and then it somehow regains the time, so that they would be reading the same when you brought the clock back. No, I don't think that would happen. The clocks would definitely read different.
Okay, so the clock is effectively one of the twins, which is now maybe younger. It's come back because it hasn't aged as much.
Yeah, exactly. I mean, that's the basis of the experiment.
Have any of our wonderful, marvelous astronauts carried one of these little wristwatches with a quartz crystal in it in their pocket, gone up to the space station, spent some time up there, a month or so, and come back to Earth, and someone looked at what the time is? It has, on the watch that he had in his pocket. That would seem to be a rather simple experiment to do.
Well, you'd have to, I mean, the amount of time you would lose even being an astronaut in space is probably like, a microsecond or something. Still wouldn't be very much.
Well, that's easy. You can make these watches have a readout of nanoseconds. You even see that on an ordinary oscilloscope.
Yeah. Well, the other problem is that the drift on a standard...
No one thought to put a little wristwatch that would read you out in the nanosecond range, or whatever, or picosecond range, in the pocket, and say, just keep that in your pocket. And when you get back to Earth in a few months, when you blast off, we have one here, and they're synchronized. So we'll see what you're reading on your watch is when you get back home. That would seem to be a relatively simple experiment to do. I mean, aside from launching the astronaut and all of the rockets and things.
I mean, it'd be easy to just launch a atomic clock into space, and then then it's pretty obvious.
If you ever decommission, say, one of the GPS satellites, and you could retrieve the timepiece there, you could actually verify whether it had lost time, which hadn't been.
Yeah, well, Mr. Lucas, he comments that, basically this has been done on airplanes. There was one controversial experiment where they sent atomic clocks going east and west, and they indeed measured different times. So this is the
Haffel-Keating experiment.
Yeah, the Haffel-Keating experiment. They did that.
Unfortunately, I'm one who perhaps has looked at this following some of Kelly's original work. Again, he has a chapter in his book about this, and it appears on the face of it actually that experiment was a complete fraud. I talked a bit about the Eddington clips experiment, and we're not just saying that maybe there's a difference in interpretation, but it seemed to be sort of fabricated, and that the clocks were drifting all over the place, and they rejected the values that they didn't like, and they average others, and so on. If you look at the original data from that experiment, I'm sorry to put it so bluntly, but it appears that experiment is not a scientific experiment, really.
Yeah.
Yeah.
Can I pose a question? Can I pose a question here, briefly? Thank you. My question is simply this, and I'm wondering about this a lot. We're going through, what is an absolute frame of reference, an absolute coordinate system, you might say? There's, people talk about we're hurtling through space at 14,000 kilometers a second, or whatever the huge number is. Okay, and our galaxy might be moving with reference to the fixed stars, which might be our best, perhaps, reference point as to some kind of an absolute frame of reference. So my question is, when we're doing these experiments here on Earth, and we're moving at these velocities with what we might believe to be an absolute frame of reference, is it a complete fiction? This is now the question. I'm sorry it's just taking so long to ask the question, but the question is it a complete fiction when we do these experiments on Earth and say, here we're going to have an electric charge that's not moving, and so there's not going to be any magnetic field which it causes, or vice versa? Well, I'll stop there. I mean, does that even make any sense? Because the electron is not stationary. It's in motion. We're all in motion as the Earth hurtles through space, and it's revolving to boot.
Yeah, now we're really getting into the relativity questions.
Now,
I would answer that to say that I, as a physical etherist, that I think that space is filled with a material substance, right? Is as solid as this pen, right? And the pen has a reference frame. So
I thought you were saying it's more like a liquid.
Well, it is like a liquid. But it's a material substance.
Okay.
It's a material substance made out of very similar stuff to us. And if it is, then it is like water, and you could say that this water has a specific fixed reference frame, right? This water defines a zero velocity reference frame, right? So anything not moving relative to that water could be said to have an absolute velocity. And as a physical etherist who thinks space is as physical as this water, then I would have to say that yes, there is actually an absolute fixed frame of reference where the ether could be considered forming the stationary frame that you're doing your experiments in. Now the question is, when we're on Earth and we're looking at an electron, is that thing in motion and generating a magnetic field, or is it really stationary? Now,
yeah, I'm saying it's not stationary.
Yeah, you're saying it's not stationary, but my answer,
we proceed with our equations and theoretical work to say, well, this is the stationary one. Like a few weeks ago, someone was saying there's several different kinds of electromagnetic fields. And I said, oh, really? What's that? And they said, well, one is where the electron is stationary, or the charge is all stationary, and that's one. And then the other one is when it's moving and so forth. And I'm saying, gee, they're going through Maxwell's equations here. We haven't observed a stationary electron, nor can we on Earth. Well, that's my question. I mean,
well, see, I would say that it is possible for us to observe the absolutely stationary electron. Now,
even though Earth is moving through space like crazy.
Yes, even though Earth is moving. Now, let me finish, okay? So let me
get
at
an
least
example
get
when you're
out
done?
my conception. Cornelius, just hold on just a second. Just at least let me get out my conception, and then you can all pile it. Okay. But my conception is that if you look at it experimentally, what's really going on, because we can only detect, say, the 24-hour rotation of the Earth in the SIGNAC experiments. But otherwise, the Earth would appear to be motionless, just based on, if you look at the experiments like GPS and things like that, they're all telling us that the Earth is stationary with a 24-hour rotation is what it's really telling us. So the only motion that you would really feel on the Earth is just the rotation 24 hours, right? So it's like we're in an ether bubble, and I kind of feel, my personal feeling, that gravity just collects the ether around the Earth, much like it does the atmosphere, right? So the atmosphere in my room here could be considered an absolute reference frame, and the velocity is in fact 0. And if we were to look at the velocity of the absolute velocity of the ether, we would find that it corresponds to, say, the rotation of the Earth, or I don't know, maybe it's 0. I mean, maybe the walls of my room are enough to slow the ether down. But although that kind of contradicts the experiments that we're seeing.
I'm trying to listen carefully, Franklin, and it seems like, in a way, you're just simply saying that the reference frame of the rotating Earth can be just taken as an absolute reference frame, but what about all the other ones? I mean, and my question was, is there a definable absolute one, in which case, here on Earth, it's impossible for us to observe an electron that's quote-unquote stationary without a magnetic field, and that's one of the kinds of electromagnetic fields that exist, and blah, 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 and on and on. So my question is your question. I mean, I don't exactly have the answer for it yet, but it's just a quiet question I have.
It's stationary.
Okay, Cornelius, you've been waiting to speak. Go ahead.
Okay. It's stationary to relative to us. And if you look at it like an example of a surfer riding a wave, if he's already riding the wave and moving along with it, he doesn't feel the force of the wave accelerating him anymore. So he can sit there and juggle balls or whatever, and except for the wind catching the balls, he won't know the difference from him standing still or not. As opposed to another surfer who's just sitting in the water waiting for a wave to come along. When that wave comes, if he's sitting there juggling some balls, those balls are gonna go. He's gonna lose them. So it's basically a relative situation. We are riding a gravitational wave, and so everything within that gravitational field to us is going to be basically static. If you're outside of the wave looking in, you'll see the motion of the wave. You'll observe the balls going backwards and not understand exactly why is that ball's not keeping up with this guy and that. But it's a situation where we are a part of that wave. We're moving along with that gravitational wave because we're integrated with it. And so that's why you really can't tell exactly what the absolute rest frame is. There is some validity to the fact that you can look at the wavelengths of light and energy coming from different directions in space. And because there's an imbalance in wavelengths in one direction or the other, there is some possible validity to being a localized center of gravity where it looks like things are kind of accelerating in that direction or centered around that direction. And it says we're not quite in the center of that wave. We're not at the bottom of that wave. We're somewhere up on the edge of it, because things coming in from us at one direction are coming from the peak of the wave, which is more stressed than things at the bottom of the wave is a different stress. So there's a different stress in the bottom of the wave to the top of the wave in this tension of the wave itself. And so if you were right in the bottom, no matter which way you looked, left or right in this case, because if we're talking about a surfing wave, there is no circular, but if it's actually in a circular well, then no matter which way you look, things coming from all directions are going to shift, phase shift or Doppler shift the same amount. So then you'll get the impression that you must be in the bottom of a local gravity wave, but you may not be able to see beyond the ridges of those waves to see if there's other local gravity points. That's about as far as I want to speculate on that. If I may speak to the concept of clocks and time dilation, basically, in my view, time is the measure of change. If there's no change, there's no time. We measure time by the rate of change of one thing compared to the rate of the change of another thing. So when you say time dilation, clock dilation, it's the same thing. We're using the clock to measure time. You can call it clock dilation, and what you're really just saying is this clock doesn't change as fast as that clock, and therefore this clock is under time dilation. Well, this clock is really just running at a different rate. And if it's as far as changing viscosities in that, and saying, well, things change slower or move slower in a higher viscosity liquid. The problem with viscosity is viscosity also causes drag. So we're really talking about things accelerating or decelerating. That the drag occurs during the acceleration, not continuously after it's in motion. So you can't really use viscosity as a possible cause for slowing things down. What you can use is you can use a variation in tension, because if I have a rubber band and I vibrate it and I increase the tension on it by pulling it apart, then it will vibrate faster for me. And if I decrease it, then it'll vibrate slower. And basically our Earth environment, being in a gravity well, is in a region of lower spatial tension. And therefore everything within it will vibrate slower. And I'm talking about if everything is made of waves, then those waves will oscillate. If you were to take a flute and play it in air, and then move into and play that same flute in a helium-filled environment, we all know how you can change your voice, the pitch of your voice, because your vocal cords are still the same, but you're working against a different environment, a different tensile environment. So all of a sudden you sound like Mickey Mouse. You know, you have a really high voice. It's the same sort of thing, except for it's all within a solid. You're changing the tension within the solid, so the vibrations increase or decrease. So as we get towards Earth, the bottom of the gravity well, we actually have less tension in this environment, which seems counterintuitive to us. The most tense areas are actually out in the middle of space, where it's very calm and very bound together. So it's all about the binding of the carrier media that makes the difference in how fast things vibrate, how fast or slow time goes, and how fast or slow light travels, because light will, again, under a tighter tension, things will move faster through that tension. So that's kind of my take on clocks and gravity wells and reference ranges.
And Mickey Mouse. All right, thanks, Cornelius. I see we also have Jim joining us. I was wondering, so Jim, do you have any comments you may want to add?
Well, I like your idea that the Earth is in its own local ether. In fact, I think I suggested to you a few weeks ago or months ago And that explains.
Yeah, it was hard for us to hear you.
All right, let me work on my audio and I'll come back.
All right. Yeah, that was a little bit better. So just unmute yourself.
Sorry?
You can just not unmute yourself when you want to speak. So generally speaking, if you're in the live room, I'll have you added to at least the audio portion of the show. So mute yourself if you don't wish to speak. Now we do have some comments from YouTube here about, say, ether is overcomplicating things. Okay, well, let me address that as an etherist as to why I think an ether is necessary. And I think that you need to do that in order to provide yourself a solid physical grounding to the physics you wish to build up, right? So you have the choice of, well, you either choose you have no ether, okay, so there's no background, or you have an ether, and so you fill space with some particle, right? Those are the two choices, right? So which one is better? So I would say that it is better to fill space with a physical particle, because we need to be able to account for the experimental facts that things like, light can travel from point A to point B. And if we don't have anything between points A and B, it's a little bit hard to see how it gets there. Now, maybe it gets there because it's an actual physical particle like a bullet, and a bullet can get from point A to point B and not have anything in between, except that we have lots of evidence that light has like a light wave, has a frequency, it has all these, they cancel each other, they have all the properties of a wave, and waves require physical mediums to travel. So, and bullets, generally speaking, don't have a frequency, don't have a wavelength, and generally don't interfere with each other. And so in order to account for that, it's better to think that space is filled with something, right, to serve as a medium. So that is one reason why I think a medium must exist. Another is to help explain what these actual relativistic effects are, right? So, James asked, is there an actual absolute frame of reference that we can rely on and do our experiments in a sensible manner, right? And if you don't have anything in your space, no ether, then there can be no frame of reference, right? There can be absolutely no frame of reference. There's nothing to reference to. But if you have your space filled with particles, then you could see that you're actually moving in an absolute sense, because you can see, oh, I just went by that particle, right? Or, so you can say that I'm moving relative to that particle. You can say you're moving relative in an absolute sense to that space. And I think a lot of these relativity questions can be answered definitively if you can establish that absolute stationary frame, which would be the absolutely stationary frame of the stationary ether. So I guess that would be my little soapbox on why I think the ether needs to be there. And it's not really an overcomplication. I think it's necessary to provide a solid foundation to the things that you're looking at. Yeah, let's see. So Cornelius has typed in a comment there. Yes, and ether thinks that that ether shouldn't have structure or parts. I mean, that's what Einstein said, that there's an ether, but it doesn't consist of parts, which I think is one of the most obviously self-contradictory statements anyone could ever really make.
Well, the only parts of it are the tension variations within it.
Yeah, and tension is a property of particulate media.
Again, tension is observed in part because we can visibly see it in particulate media. Tension continues all the way down between the particles. It's the tension between the particles that make the particles interact. The particles themselves are nothing but concentrated points of tension. Just like
tension, like a rubber band. I mean, if we can agree, first of all, that tension is what happens in a rubber band when you stretch it. That's tension.
Okay, but
and ultimately, physically,
So,
Go ahead.
if you stretch the rubber band, between each molecule of the rubber band, there's a tension field. There's a tension between those molecules. You make the rubber band one molecule thick, and you still have some tension between adjacent molecules. Then you go on down inside the molecules, and what's holding the molecules together is tension between atoms. What's holding the atoms together is tension within the spherical nature of the atom. So basically, it's all tension waves being concentrated. It's all about the bonding strength of any particular location within the media or within space. So it's a concentration of tension that we recognize as particles. And it's the tension between those recognized concentrations of particles that you're recognizing as tension within the rubber band. It is still tension going down to tension, going to down to tension, and more and more finer detail in the granularity of the tension patterns.
Well, definitely, I would agree with you that tension does certainly exist. Tension exists between the molecules. Tension exists between the atoms that make up the molecules, and tension exists between the protons and electrons.
And tension exists
that are
within
holding those things together. But the question is, what's causing that tension, right? Would be the
Waves.
ultimate question.
Waves. What's causing it? What you're asking is not what's causing that tension, but what is causing that tension to behave point-like and like a hard particle. And that is basically the concentration, the intensity of the tension is being focused towards a point, and that intense tensions point interacts with other intense tension points, because if you stretch something, if you increase the tension to the point of the media not being able to carry tension anymore, you wind up with a hole in space where waves can no longer travel. And so if you try to bring two extremely highly tensioned points together of wave point, if I drop two raindrops on the surface of the water, I see this tension wave pattern in the surface of the water. If that tension gets so strong, eventually that water's surface will break, and I'll get a drop that'll come away from it. That only happens in material items. That can't happen in a continuum. If in a continuous space, the only thing that can happen is that tension can keep on getting tenser and tenser and weaker to the point where eventually it cannot carry the waves. And so when you try to bring two of these wave patterns together, then what you get is this is already at the limit of the tension capability of the media, and you bring another one together, and this one's at the limit of the tension. And both of these are wave patterns, and so this wave pattern is actually flowing past and going around this wave pattern, because it's just like two raindrops on the surface of water. You see that the two raindrop patterns actually overlap each other. You're not just looking at points, you're looking at raindrop patterns, and they overlap each other. But if they come together and they're both already at the surface, their centers are both so strong that they're already at the center of at the maximum tensile strength of the surface of that water, they can't come together, because as they come together, the surface will break, which means that there's no way for the waves that they're part of to move any closer together. So they will get deflected away from each other. And it's basically the rest of the surface that's actually causing them to move away to where they're more accepted, where they can move more easily. So that's why they behave like they're solid little balls, because they can't go together, because they've broken their carrier.
Okay, well that went I was trying to get to the question of what tension is. Now in conventional mainstream physics, the tension is caused by the attraction of positive negative charges. So that's why the proton attracts the electron, because there's this Coulomb law, and that's what actually creates the tension. So if you put the two things together, they're very tightly bound, and you pull them apart, they like a rubber band, they want to come back together again, right? So I mean, ultimately, that's, I think, if we can all agree, the source of tension, which is basically the electrostatic attraction. Even probably in a rubber band, mainstream would agree that what you're doing is that the molecules of the rubber band are attracted to each other by electrostatic forces.
But what I'm saying is tension is fundamental. All these other things are built out of patterns of tension. It's the tension that is the fundamental thing that's happening here. The tension is the only thing that's fundamental. The desire, the actual characteristic of the media to remain together, to remain bound.
Well, I suppose you could stop there and say that, but that's basically saying that you can't explain electrostatic attraction. That's just that's.
Oh, no, absolutely. I can explain electrostatic attraction. It's easier to explain gravitational attraction, however, than it is electrostatic attraction, because electrostatic is already a very complex wave pattern. Much more gravitational attraction is much more like the two raindrops that I just explained on the surface of the water. Those, if you'll notice, are gravitationally attracted. They always attract each other to the point of the exclusionary principle where they can't go any closer together. But that's gravitational attraction. Those two raindrops on the surface of the water in a two-dimensional field represent what a gravitational field would look like in reality. And we're not talking about, the Earth vibrates like that. Every atom, every molecule, every particle in space has that raindrop characteristic to it as its fundamental mass core. And this is basically mass. This raindrop characteristic, this spherical ring characteristic, is mass, because you can prove that to yourself by taking a bobber on the surface of water and dragging it across the water. Just pull it across the water on a string, and then you can find a way of making that bobber bob up and down to interrupt the water and to create those circular rings around the water. And then while it's bobbing up and down, try to accelerate it and see if it doesn't take more force to accelerate, because you now have to accelerate not only the bobber, but the entire wave pattern that bobber is part of. And the bobber is only there as an object that we can use to simulate and maintain those wave patterns, but it's really those wave patterns that are the inertial characteristic of the tension pattern within the water. So it's really that's what mass is. It's the concentration of tension into a point to create a particle.
Let's see, we've got some other comments out here on YouTube here. So, there are some people think that waves can travel without an ether. And of course, I would ask, how? In order to have a wave, you have to have something which is distinctly measurable. And I think, that's what Hertz showed in his original experiments. He set up a standing wave in his laboratory, and he could measure and actually identify where the nodes of high intensity were and the nodes of low intensity were. That was a very, very, physical proof that the radio wave is in fact a wave, right? That you can find the nodes. There's a high intensity node, low intensity node, high intensity node through space. You can physically find that thing.
See, that concept of that problem, the idea of that waves can travel through nothing, is basically kind of a repercussion of people overcomplicating what ether is too, making it structured, making it particular. But if you consider ether as nothing more than a tension field, then you don't have that complications. And waves can move through a tension field, but they can't move through nothing. It's a problem that people say ether doesn't exist because of all the complex concepts of ether that have been put together. And I think that's why people are just saying, well, waves can move through nothing. Well, in their mind, ether, they're moving through something, but they're not moving through anything with a structure.
Well, that view which was expressed by that commenter is in accordance with conventional scientific views. But I'd like to know if that commenter would conceive of waves traveling without an ether because of their particulate nature. What's the reason that he neither conceives of an ether nor thinks it's necessary for waves to travel through one.
I mean, you can think of that. I mean, anyone can feel free to think of anything. You know, I can think black is white, right is wrong, and, you know, things like military intelligence. But the thing is that what's the easier thing to conceive of, right? The easier thing to conceive of, in my mind, is a particulate medium, because we see, you know, sound as an analogy. And that's a very easy analogy. I mean, I don't know why you would think that's complicated. I mean, how complicated is particulate medium with a compression wave running through it? That's not very complicated at all, right?
But the interesting thing is that probably most of us in this environment would agree with you. You know, that seems patently clear. But yet the reality is that we are a minuscule minority of scientific analysts who think this. The vast majority of the populace out in the world disagree fundamentally, and they hold this view that you are saying now is illogical and difficult. So, you know, again, we're back to the conspiracy type thing. You know, why are people believing this? Has it become orthodoxy and they daren't question it now? If it's so patently unclear that this should be so, it seems almost illogical. By the way, one other thing I might just mention is that you know, I do conceive of an absolute space. I suppose it's a bit of a theoretical concept. It's like I call it maybe the universe at large, whatever that is. But you know, I conceive of that, and I conceive of ourselves as moving through this at all these various speeds and so on. But nevertheless, there is a local environment of ether in accordance with my thinking, which effectively is moving with us, or indeed, as you said, Franklin, is not moving in our rotation, our daily rotation, but is being carried by the Earth-centered inertial frame, if you like. So therefore, we do experiments with electrons, and we appear not to get a sensible magnetic field. However, we are moving against this universe at large, if you like, and I conceive actually not as some of the classicists conceive that the ether was an absolute frame, but and that we were moving through the ether. But conversely, I conceive that the ether is actually moving through the absolute frame. The absolute frame is really independent of ether, and you have local ethers which are, you know, dependent upon, I think Cornelius talked about the gravitational field being analogous to the surfer on the wave going through the thing. That would be one way of looking at it. So there are various ethers which are determined by the gravitational or magnetic or electromagnetic fields of the body, which is actually carrying the ether.
Yeah, you mentioned the concept of local ethers, and that's kind of like what I believe in. It's like if you're able to create your own little ether bubble, then you would be immune to, say, inertial effects, right? That's kind of like if you look at like some of the UFO theories, they say that the little spaceship there creates a local, you know, ether bubble, so that, you know, the spaceship, it can go to like 90-degree turn, and the occupants don't feel anything, because they've created their own absolute frame of reference inside of their own little spaceship there. And the Earth, I think, is kind of acting as its own local ether bubble. The moon probably has its own ether bubble. The sun probably has its own local ether bubble. But out in empty space, there probably is something that we could probably call more of a galactic frame, I would think. That is, if you believe in there being such an ether, and that there being possible that there be local ether bubbles, I suppose.
Yes, and I think it needs some critical field, some critical value of field, say gravitational field or whatever, to create this ether bubble. Because as far as we know, that very small items don't create ether bubbles. Like the Sagnac experiment, for example, is a demonstration that the spinning disk does not have its own ether bubble. It's actually experiencing an ether wind through the ether bubble on the Earth, if you like. It's not actually dragging the ether. And similarly, in a moving train or in a moving aeroplane or something like that, that is actually not dragging its ether bubble with it. So there seems to be a necessity for some critical gravitational or electromagnetic field in order to create this ether bubble, which will be carried.
Yeah, but what I find interesting is that all those experiments, point to the Earth-centered inertial frame, which is that we can detect the SIGNAC experiments can detect the 24-hour rotation. And I think GPS treats that the same way as well. GPS has to do all of its so-called relativity calculations, assuming that the Earth is pinned to the center of the universe around its core and is rotating once every 24 hours. So that when it sends its signals, it has to know that New York is traveling, that direction so fast in order to actually pinpoint you on the Earth. I mean, that's what it has to presume, right?
But if you look at the Michelson-Gale experiment in the late 1920s, that basically does show up the spin of the Earth, all right, but not exactly. There's a very small, some percentage differences. And one way of accounting for that is to weight the effects of the spin.
Whoops, somehow you got muted there.
Sorry, I just pressed my button. I'm getting excited, banging my hands down on things. So to weight the value, maybe like it might be 99.5% proportion of the spin of the Earth, and also the very much the residue which would be accounted for by the non-perfect inertial reference frame of the Earth in its annual orbit around the sun, and to indicate a sort of a tidal locking effect, owing to the effect of the other planets, particularly the sun and the moon. And that might affect for maybe 0.5% or something like that. But if you actually weight those up, you get a value which appears to be almost dead on with what Michelson-Gale got. So it's not 100% the spin of the Earth and 0% the rotation of the Earth.
That's it. That's very interesting. I hadn't really heard about that. And I think that's interesting from, a geocentrist point of view, because literally the geocentrists feel that the Earth is in fact the center of the Earth, and that, they feel that not that the Earth doesn't even rotate, that the reason why, say, the Michelson-Morley experiment measured zero velocity is because we really are at zero velocity. And that if you had sent...
That's true. However, when it comes to observing something like the slippage of the Earth through the ether, if you like, in its daily rotation, what they just say is, we explained that the ether is moving in the opposite direction relative to the Earth. The whole universe ether is moving around the Earth in that way. So in one sense, when you get a practically zero value for ether slippage, they say the Earth is stationary. And in the other case, when you get a practically 100% value, they say, well, yes, that's fine. The ether is moving the other direction. So it's an example of how all people, explain the phenomena in terms of their own philosophy. I mean, the non-geocentrists are doing it as well, admittedly, but certainly the geocentrists are doing it.
I don't deal with any of that, because basically we're not slipping through the ether, and the ether isn't slipping through us. If we're actually consists of wave patterns, we're propagating as coherent patterns through the ether, basically. We are only defined as wave patterns in it. So when the Earth moves through the ether, the Earth is actually just a propagating pattern. It's like the raindrop on the surface of the water. If you drop a raindrop on the surface of a slowly moving stream, it will have a tendency to not necessarily move immediately with the stream. It will stay put for a while until friction takes over, because water is a composite material, which was not a pure again, the energy goes into each individual molecule, which is actually a pattern of ether itself, within the ether itself of energy.
But I think what Ian is pointing out is something you can't explain, right? If it would appear that the Earth is picking up some fraction of its potential movement, and if what you're saying is true, then that should really be zero, or you can't explain it, right?
No, because each individual particle, each individual atom, each individual molecule is a tension point within the ether, and the tension is always being redistributed. So why would you say it couldn't be explained? It would be a lot like because if I put this raindrop in the middle of a wave moving through the ocean, the tension on the top of that wave at the maximum point is different than the tension on the minimum on the lower part of that wave, and so that difference in tension is going to cause my raindrops tension pattern to move towards towards the area of greater tension, because that's where the raindrops wave pattern is going to move more easily and faster. Again,
now the problem here is that I didn't really understand that's a very complicated way of explaining things. I was just wondering, Ian, did you understand that? Because I didn't get it at all.
Well, look, it's one model, and I could parse it, but more fundamentally, I mean, the very small picking up of the motion through the revolution is a second order effect. But more fundamentally, let's say you don't pick that up. You approximately don't pick that up, but you approximately pick up 100% of the slippage through the daily rotation, which is evidenced by the Michelson-Gale experiment, where you shine light through a piping in opposite directions, and you're able to pick up the projection of the spin of the Earth onto that latitude where the experiment is done. In this case, it's done in Illinois, and reported in 1929. So you have to explain that, Cornelis. If why in one case do you get the full effect and in the other case you don't?
I'm not exactly sure I followed what you're saying there, Ian.
So it appeared to me that you were maybe explaining the null result, let's say null result of the Michelson-Morley experiment by your model there, which Franklin was having difficulty understanding, and I mean, I could spend a lot of time on it, but I'm willing to accept it's your explanation at the moment for it.
Okay, well, however, the Michelson-Morley experiment,
that would appear to be contradicted by the Michelson-Gale experiment.
Okay, the Michelson-Morley experiment, not the Michelson-Gale experiment. I have to review what those are. But the Michelson-Morley experiment would be done within the Earth's atmosphere and within the same gravitational environment. It's just a very small area in which they did it. So basically, the tension throughout the entire background, the background tension within which all these molecules exist and atoms exist, is fundamentally the same tension. So it's like playing a flute, and if you play 100 flutes and they're all in the same atmospheric pressure, you're going to get the same tone. Or same pipe organ, you're going to get the same tone. You change you move to a location where you might have a colder area in the room, and the air density is heavier, and the tension within that media is different. You'll get a different tone. That's why. So it's because the experiment was done within the same environment. In the case of the Michelson-Morley experiment, the Michelson-Gale experiment, I am not 100% sure I've got that one clear in my mind as to what that is. You might have to explain that if I were to try to come up with a solution for that. Is that the one where they have the actual, it's actually rotating?
Well, no. Analogously to the Michelson-Morley, they're endeavoring to use the motion of the Earth to provide the rotation through the ether. So in the Michelson-Morley experiment, obviously, as you know, they just have an interferometer there, and they're just saying, well, it's being carried through space at
At the orbital velocity they're looking for.
Okay.
Yeah,
Okay.
but with the Michelson Gale one, they have piping, which is like a couple of kilometers, a rectangle of piping.
Okay.
And they have the
With the fluid in it? Is that
It's
the
a
one,
light ring of some sort.
is that the one with the fluid motion in it?
No,
no, that's the FISO. That's earlier FISO with the
Okay.
drag. But this is just in air. It's almost the same as the Michelson-Morley, except it's a big Sagnac type circuit, if you like, and you're shining the light around and having it recombine and seeing is there any fringe shift. Now, if there isn't, well, you haven't detected any motion. But if there is, you've detected motion. And what is that motion? Well, theoretically, it's the motion of the spin of the Earth, which is carrying this large Sagnac type circuit around in its daily rotation. And hey presto, if you work out the formula for the fringe difference and so on, and the circuit and the parameters and the speed of the Earth, the angular speed of the Earth in a day, you find that it gives approximately the correct fringe shift.
So it's largely a large optical gyroscope, then you're saying?
Yes, one might say that. Yes.
Yeah, and it was the size of it fairly large?
Yeah, as far as I can remember, it was something like maybe the larger leg was probably over a mile long, and the shorter one might have been half a mile or something like that.
Okay, yeah, that's a lot like an optical
An optical gyroscope.
Yeah.
It's the same phenomenon. It is.
And it's because you basically are moving in a single circular direction with your light, or actually two circular directions, but one being against the rotation of the Earth and one being with the rotation of the Earth.
That's quite correct.
Yeah.
But I mean, according to your own model, I suppose this is what we're asking in a way. According to your own model, how does that show up a full value?
Okay,
Where
because
in the case of the orbit of the Earth, it doesn't show up.
Okay, because when you're moving with the rotation of the Earth, remember the Earth. If the Earth is actually these focused ring patterns, those focused wave patterns are basically every time you enter one. If your light is entering one, it's accelerating, is decelerating, and accelerating, because every wave you start out with a gentle wave, and then you get to a stronger and stronger wave at the center of the particle, and then you get a weaker and weaker wave. And waves are not just point particles. Particles are not just point particles. They are the center of a wave pattern, like the center of the raindrop pattern, and they extend infinitely into space. They get weak really quickly, so we think they're just in a very small area. 99.99% of them is in just this little dot, but they still get weaker. So if you have light moving through this field, it's like moving into a gravity field where you have to, instead of moving just straight, you have to move up and down. You're riding this wave, that you're accelerating into this wave and you're decelerating out of this wave as you go by. So it's like if you take the average of it, the power of it, it's like going into a gravity well and out of a gravity well. Well, if these gravity wells are moving this way and you're going in and out of them, and you're going in and out of them and you're moving with them, then it's like you entering a town with your car going 50 miles an hour and the car is going 40 miles an hour. It's going to take you a lot longer to get through that town. Okay, and you're also, it's not the length of time it takes you, but it's an acceleration followed by a deceleration that slows you down. And you can, if you're going the other way, you're actually doing the accelerating first and then decelerating more. Your acceleration is much steeper, but there's a limit to how fast you can accelerate. It's like like a swimmer going, back and forth up a stream. If he's swimming half the speed of the stream, or twice the speed of the stream is flowing, he's going to get up and back. But the closer,
so we're getting a little bit close to the our 2-hour limit here. So
okay, the slower he goes, he's going to reach a point where if he goes too slow, the stream is he's never going to reach the top of the stream, his goal, and he's never going to come back. So he's going to be stopped. So it's really the fact of you're moving either with these waves or moving against these waves in a circular pattern. These waves are the Earth moving in a circular pattern, and you're going in and out of these gravity wells, microgravity wells. Every particle is really a microgravity well, and the Earth combined is a humongous gravity well. It's a combination of all this, but it's the going in and out, the acceleration deceleration rates that make it take longer to go one way or than the other, because you really travel a greater distance.
did that make any sense to you, Ian?
Well,
I mean, I kind of had to cut Cornelius off because we just cut down.
It may, Franklin, be another way of looking at the thing. I mean, the way I look at it is that more simply, that the the orbit of the Earth, the annual orbit of the Earth, is very approximately inertial, but in comparison with that, the rotation, the orbit of the spin of the Earth, the rotation of the Earth, is non-inertial. You can find sensible effects by looking at things like the Coriolis effect affecting different atmospheric circulations in the northern hemisphere and the southern hemisphere. You can actually find some small effects owing to the Earth's the Earth's daily orbit, but it's very, very difficult to find sensible effects owing to the Earth's annual orbit. And it's not simply the velocity. I mean, the velocity is 100 times or something. In the case of the orbit of the Earth, through the absolute.
But you're saying that the Michelson-Gale experiment does pick up some of that orbital component.
It picks up nearly 100% of it. Yes.
Yeah, and it would, because it's a gyroscope. And the thing of difference about the Michelson-Gale and the Michelson-Morley experiment is the Michelson-Morley is an over and back experiment. So you're traveling in one direction against the waves, and then you're traveling the other direction with the waves. So the average is going to always be the same. Okay, as opposed to the Michelson-Gale experiment, where you're going around, one beam is going around with it, and one beam is going around against the direction, and you're comparing the two beams to see, well, what the difference is when you get there. So that they're not really an over and back. If you were to take the one beam and go around and then turn it around and come back, you wouldn't get the results. They would nullify each other. And it's like, instead of going around in a circle around back, the Michelson-Morley experiment is simply going straight across and straight back.
Well, so it's true that the Michelson-Morley experiment is a second order experiment, whereas the Michelson-Gale is a first order, which has a much greater sensitivity to showing effects. However, with modern equipment and sort of masers and so on, they have verified that there's a very, very, very small effect from the Michelson-Gale, much, much less than one would pick up, had we measured a sensible proportion of the movement through a static ether. So that can basically be ruled out, I think.
All right. Well, I think we've come to the end of our time here. So maybe next time we can talk a little bit more about what this Michelson-Gale experiment is. So maybe, Ian, if you could maybe look into a little bit more about that specific experiment, maybe bring us some references. We could maybe talk about what the experiments really show, because I'm really more interested in what the experiments really show and trying to fit our world into that rather than to trying to decide the world is like this and then trying to fit our experiments to that. So, but that will bring us to the end of today's time, and hopefully we'll see you here same time, same bat channel, same bat time every week here on Saturday. So thanks for everyone participating in the live chats. But that will do it for today's
Thank you.
show.